Welcome back to another video tutorial of ProSap. I'm Antonio Rimena, as you already know me. And in today's video, I'm gonna teach you how to model and perform analysis and checks on a steel structure. Basically, most of the commands will be the same that you already have seen in previous videos, but we are just gonna use some particular commands or just something more that I haven't shown you in concrete structures. So first of all, we are gonna go structure data sections and define the sections that we are gonna use. The first one will be a section for the columns, so an HE. We can go 180 and go apply. I'm probably gonna be quite faster than usual on some commands, just because I think you already know that, and I don't want to bore you just repeating that you have to click apply, that you have to some minimum details, let's say like that. So let's go. First section is for the columns. I can choose the name to help me. Apply. The second section will be for beams, generical beams. Then we will see later that we need different kinds of section for different kind of beams. Once again we go on profili semplici, and here we can check IP. Maybe just 120 will be good. Apply. On number 3, we are going to define another simple profile. No, okay, let's use profilo accoppiato. It's just the couple of single profile, like 2L, like that. And we can go 40 per 4. Here, when you create a profilo accoppiato, a coupled profile, I think it's the proper English translation. From this window, you can start inserting some kind of properties. In the specific, coupling distance is the distance between each profile, everything in millimeters. Stiffening bracket distance is the distance between each joint, each union of this profile. So 500 is quite too much, probably 50 is something better. 50 millimeters is 5 centimeters. No, okay, maybe this is no, maybe 500 was correct. And stiffening bracket is the dimension of the joint, and with this thickness that usually is the same dimension of the coupling distance. So we can go OK, apply, and as last I want to create a circular section, so it cannot be found nor in profili semplici or profili accoppiati. It's just a generic section like this, and on intended use we can select for steel elements. This section is going to be used for bracings, and so we need something only tension resistant and not compression resistant, basically. So a circular section with a radius of 2 centimeters should be okay. And okay, we can see bracing. Okay. Yes, apply. It's useless to specify that in the name, because the software automatically adds to the name the kind of section and the parameter. So we can go apply, and I think you see that the section is now blue. It means that it is intended for steel. And okay, we are fine with the use of sections. Then some other things you can check in the section tab is that when you use a still section, a still profile like this, you can then move to these three tabs, data sezione, so basically section data, in which you can find numerical properties of our section that are going to be used in the calculation, like the total area of the structure, the area for the shear force. Right now is 0, but it's going to be calculated later. The torsional moment between for each axis and every other parameter. As I already probably showed you, this kind of data are also available for concrete sections, and this percentage is the stiffness percentage for each kind of action. This is axial stiffness, torsional, flexural stiffness, and torsional stiffness. In progetto acciaio, okay, we can move on. And here in verifica acciaio, you can basically see which is the class of your section. You can choose between class 1, 2, 3, or 4 based on the normative. And usually it's by default set on automatic for profili semplici, I mean for the profiles that are already in the software. And also there you can go check some parameters, some values that are used to do the analysis. Also in impostazioni avanzate you can click and select different kinds of check for the singular section. Okay. So basically now we can go model our structure. So first of all, we're going to create a couple nodes. The first one on the origin. So we can go OK. And the second one, let's say that we have 5 meters between a column and the other. Now we can go D2 from node and just select 0, 0. We just want to extrude the node with the section, so this zeta, delta zeta, will be something like 3 meters. We go OK. Okay, they probably here, okay, we should have, no, okay, we have section number 9, we go with the first section, and we set properties and apply. Now I want to copy that on the other node, so I go with the command copy and move, click on this node, click on the other one, and go OK. Let's see, I want basically to create now a portal with 2 columns and an upper element that we're gonna use this command to create, so trusses. This is a wizard, a tool that the software offers to automatically create full structures like that. And basically, okay, we can use this. Before go OK, you should check the values that are indicated in the image, like height, HE, HI. This means external, internal, I think. So if you go trusses, you can check that. Exactly. HE is external height, HI is internal height. And number of elements, let's say like that, of our structure. So we can go OK. We click on the first and on the last node. And then number of sectors 6, I think it's fine. You can go 50 and 100. It's just numbers. I think that they could be fine for our example. We go OK, and now we see that the software automatically generated that. One thing that we should do is for sure to change the section, because right now if we go on, if we check this, we have the same column section for everything. So if I go solid view, okay, maybe this is quite too much, too big, too heavy for its purpose. So we are going, let's say the lines, okay. I don't know if I never told you, but if you go hidden lines, you can move with the less transparent and more transparent to basically decide the transparency degree of our view. In this case, I like to use something like that, so I can actually see the element to click, and I also can see which kind of section it's using. So we are here, and we are gonna select, I think this could be fine, and set reference. The material is fine, everything else is good. And now with near, we go click on the other elements in which we want to assign the same section, that are these ones. Only the superior and inferior current, because I want to use another section for the inclinate elements, oblique elements. So right click, assign reference, and this is fine. Now I can edit these elements and use this section, the number 3. So I can set properties of apply. Actually, this kind of elements, the elements between the superior and inferior current, can be described as truss. They are truss elements, because basically they are just supposed to react to and to support and axial forces and not shear forces or bending moments. So we can change that from beam to truss. You see that when you go truss, you lose some number of properties, because with beam you can define basically the release codes, the release nodes, the degrees of freedom release for each node of the element. Instead, while using the truss, they're basically redefined as actual force only. So, okay, we just have to change these two things. Once again, as a set reference. Once again, near, select this, all the internal elements of our top structure. Right click, assign reference. Okay, and this is the first thing to do. Another thing that we should, okay, let's check this thing. If we go back on wireframe, we can see that truss elements have bigger frame respect to normal beams. So when you see that the element is thicker than the normal, it means that it is a truss, or it is a foundation element, as we saw in the previous video. But right now we are not using foundation elements, so you know that if you see a thicker element, it's just because it is a truss, and so it's basically responding and supporting only axial forces. So its degrees of freedom are free. It has zero stiffness for shear forces and bending moments. Now we have to copy this and so copy and translate the whole structure in its orthogonal dimension. First of all, we have to rotate our columns. So, because we want our columns to have their strong flexural moment outside its plane. So we can see like that. We can see from the solid view that right now our columns have the strong bending moment inside the plane. So we want to rotate them of 90 degrees. So 90, set. You can see now that it's rotated. We can select this, right click, assign reference, and now they're all rotated. Fine, we can move on. No, okay, before move on, another thing that we should do is define the elastic boundary, so the external boundaries of our structure. Here we can apply different kind of reasonings. First of all, we can use the external boundary as fixed, so we can just fix it. I prefer to work in wireframe like this. And for this one and also for this one. But now we know that usually when you model steel structures, basically you can consider the weaker degrees of freedom, like as I said, I rotated in this moment the column of 90 degrees in such a way that its major bending moment resistance is outside the plane. So the one that is inside the plane can also be considered like zero, basically. So usually you can or use a kind of external boundary in which you don't check the ty. Okay. It means that this external boundary has no boundary for the no yx for the shear actions in x direction, so in the plane. And this is the first thing that we can do. So use external boundaries in a way that we can assume that our columns are not resisting in the plane of our portal. Another thing, so this is an option. Another option is to consider the external boundary fully fixed, like this, and then inserting a release on the node of the element. So in this case, I think this is the E node, it's the first one, yes. When you use them, you can see a little ball, let's see like that. That indicates that an internal node release is applied, and these are each degrees of freedom that is released. So, for example, if I use only n, it means that our element is released for axial forces, so it doesn't have any kind of axial forces on it, and it resists just to shear forces and bending moments in this node. It's just a degrees of freedom release for the node, not for the whole element. Of course, if I put on each node, it becomes on the whole element. In fact, POSAP it's warning me that this should not be done. Okay, so back to us. this is not what I really want. I want to apply the release on the plane in which our actual structure is. So we should use v3, I think. These are for axes, so n should be axis 1, axis 2, axis 3. As I already showed you, to be sure of which degrees of freedom to release, you can go on preferences, visualization option, and select this preferences elements option, and we go on the two local axes. Okay, so they follow the RGB, so red, green, blue rule. So red is 1, green is 2, blue is 3. So in this case, we should release the v3. So the CR actions on local axis number 3. In this case, consider with the in-plane actions. Now we can close these because they're quite confusions, and we're fine like that. So basically, it is the same to have this situation or this situation. Usually, in order to have a more clean model, it is better to apply degrees of freedom actually directly on the external boundary. So we go like that, and now we're fine. Our the rest is truss, and I think that now we can go copy it. So we select all, copy and move from this to, we don't want a translation in zeta, we just want a translation in y. So if the initial node is 0, the final node could be something like 400, I don't know, let's say 500. Okay, let's create a box, basically. Let's create a couple of them. Okay, now we have our portals. They're all the same, and now we just have to connect them with other elements. Okay, maybe they are too far from each other. We should okay, go and do, and if the same common for 500, but maybe just for 3. Okay. Seems more realistic to me like that. And then we just need to join them together. In order to do that, we are going to use for sure other beams. So the do element with the first command, we just create elements node to node. Okay, before doing that, we want to create them directly with the correct section instead of create them with the wrong section, modify it, change it, assign, etc., etc. So we can go set the reference and just use beam kind with the IP 120, rotation 0, and okay, and now we can go save. We can set. I was thinking about also apply release nodes for the bending moment in the vertical plane of the beam. Okay, let's do that. This kind of release is always M3. So when you have a horizontal beam M3, it means that you're releasing the degrees of freedom for the bending moment in the vertical plane of the beam. And okay, this usually is done because with steel structures in which you have a huge number of elements, you often have a lot of frames like that in which you have a lot of elements, as I said. basically, if you fix each join between every element, the structure is going to resulting very hyperstatic, and also actions are going to be very high. So to release some degrees of freedom for nodes is just a way to low down the entity of the actions on the whole structure. And okay, we can set the reference. Now we can create, and we can create with this command as we said. So we can go from here to here, from here to here. Okay, let's say that, okay, I just create two of them, then I can use this command, copy and move, and I copy here, okay, here, and so this should be good. Fine, now as the last thing, there are beams, that's good. As last thing, we can model the braces. So once again, we go on set to reference. Now we want to use trusses because the bracing between one column and the other are basically braces for the factor, so they are not getting shear and bending forces, just the actual ones. So they are trusses, their section are going to be bracing circular, and okay, we're fine like that. We can go set reference and then create. Okay, click the from here to here, okay, and from here to here, okay. In this case, we don't want the elements to intersect each other. So, so basically it's fine like this. If you split up view, we see that and it's totally fine. Once again, then I can use the copy and move. So from here to here. And I think we're good. Okay. Now what we should just model are the panels on the floor, on the roof. So as last thing, we are gonna create a polygonal floor panel, and once again we can just create one. Okay, we want to create a panel between each in each space, basically between each beam, in a way that they can transfer the load correctly. Well, actually, it depends on its orientation, because if the orientation is here, so if they bring their load to the main structure, we can also create just a single one from here to here, like that. If instead, if you want to order them in a way that they are basically loading the beams, it's better to have a single panel for each single field. Okay, for the moment, let's just create one for each field. So we have one, we have created one, it is selected. You can copy it from here to here, and from here to here. We cannot copy anymore here because the orientation is different, but we can basically not select all, select 1, 2, 3, and copy on the other one, and then repeat the process. So 1, 2, 3, 4. Okay. Close. Copy and move. Select all the three and copy from here into there. Here we go. Now we have our structure. Our structure that should be complete. I think that we can go. Well, for sure we can save it because we didn't save it, and it's better to do that before go with check structure data. Well, of course I can go check structure data. The program is gonna the program is automatically saying that I have to save it. So and okay, we are fine. We ended our modulation. And we can go on. So the next step will be move to the load assignment context and proceed as I already showed you in the previous videos. So go on load data and create all load cases. So we can go on load cases help and click on the first one that add all the typical action structures. So permanent, variable, and seismic actions. We want to use dynamic analysis, of course, yes. And okay, after that we have to move to seismic load cases, and here we can basically select the importance class of the structure, which is its location. If you don't have, of course, you're not in Italy, I'm gonna use Ferrara as example. You can just create this by your own, so we can go OK just to be faster. You just need to do yes on everything. And yes, this is it. Basically, in steel structure, if you want to add load, you can do as shown in the previous video. So you create the generic load, then you go edit on an element. Okay. Before you assign the loads defined in generic loads, you have to create one more load case. So we move to the first free slot and create a generic level load action. Apply. Then with the edit you can access to the property table of the loads for the specific element. You can move here, etc., etc. We are not going to do that right now. Well, one thing that I should probably explain you is the way to insert the wind loads, because wind loads can be applied in two different ways. The first one, you can just simply calculate by yourself and then apply them as linear loads on linear elements. Otherwise, if you prefer to calculate them as pressure loads, you have to know that the pressure loads can be applied only on panels element. So in order to do that, we have to do something specific that is basically copy each floor element that we already created, transform it to panel and assign the pressure. So a quick way to do that could be use the property command to select all floors and roofs. Now we can copy and move them like 3 meters up. Now we can go edit one of them and click on the here, use as a panel. When you use an element as a panel, what does it change? It changes that it has no stiffness, so panels has no stiffness, nor inside the plane, nor outside the plane.
and the only use of the panel is just to distribute the pressure loads. So then you can you have to change material because we are gonna move them back upper the real floor, let's say that. So we're gonna have two overlapped elements basically, and we don't want to consider them twice in the self-weight load case. So for these for the panels we have to change material and use the last one in the archive, that is a material with no weight, basically no specific weight. It also has an infinite stiffness, because this material can be used to create rigid links, as I showed you already. But because panels has no stiffness, this basically it's useless, the infinite stiffness of the material. What we really need is the zero self-weight. So click on this, change material. The thickness is not that important, but we can use 0.1 just to remember that is like a support panel just to distribute loads. And then we're fine. We can set the properties and apply. Right click, assign assign material. No, okay, what's the problem here? That I changed them to panels, so I'm not allowed to basically assign the definition from floor to panel. So you have to do this one-on-one. Okay, basically I have to go on the other and click users panel, maybe assign function. No, okay. Users panel, we have to do that for everyone. We can just change the kind of element and then we are gonna use the assign properties for material and thickness. Okay, you see, now that all the selected elements are of the same kind, so panels, we can use assign reference. And now they are all last material 0.1 thickness. Perfect. As last thing, I have to move them back. So with the selection still active, not copy and move, but just move. We have no nodes basically because we just copied the floor elements, so we cannot click here because we have no nodes, but we can just insert a minimum sign there. Okay. Now we should do the checks again, but before doing that, it is proper to go on Edit, Advanced, and here we should activate the check on check structure data allow overlapped elements. This way, usually overlapped elements are not allowed. So if there are some overlapped elements in the model, the check structure data will give me a warning and stop me for the analysis. But if we do this, basically the problem know that we want overlapped elements. And okay, this is it. One last thing that probably I forgot to mention is that for bracing elements, I use the truss, because truss, as I already said, is the element that only act with axial forces. But in the specific braces in steel structure, you only works in tension with tension forces and not compression forces. So ProSUP has a specific kind of element that is tense truss, that is a nonlinear element, so a truss that only work with tension. On the opposite side, we have no tension truss that are nonlinear truss that works only on compression. But for this kind of braces, we have to use tense truss. We set the properties, but as before, I think we cannot assign. If I assign reference, okay, it works. So basically, I can go properties, the two element trusses, okay, sorry. I cannot do that because the upper side we have trusses, but we want them to work also on compression. So we can do that. We move on X plus view. We hide all of this. Display hide. No, okay. So okay. I had to select something more. Yes, all of this. So box here, display hide. Now, if I use property truss, I'll have only braces. Right click, assign reference. If I go edit on the other one, I can check that it worked. They're all tense truss. And now we're fine. I can go back with all on. And now our structure is ready. We go again on structure data. We have the warning of overlap double element selected, but we shouldn't have this because I used advanced. Oh, wait. Okay, so probably the warning is already given, but this is not a problem. Okay, the important fact is that we know and the software know that this is something that we wanted. So once again, check structure data. No. Okay. Now on load assignment, you can assign pressure loads. Let's say that we create a pressure load, one new, uniform or non-linear, it's the same, called wind. We just have a random value. I just wanted to show how to do that. Here, what I suggest you is to hide the floors, display hide. So what it remains are just the panels. Now I can go here and assign that. Okay, to assign the wind, we need to first we have to create load cases. Load cases for the wind. So we can use load cases help and click on wind, or we can just go on load cases and create them one by one. Basically, we can also do that. The software asked me if I want to apply load to visible different panel elements. I suggest you to click no. Basically, this is an automatism that the program can use to instant apply pressure loads with specific names only to vertical panels. So I prefer not to explain this to you, but it's every time it's always better to do it manually. So we can go no. If we go check load cases, now on the end we're gonna have wind load x plus, x min, epsilon plus, epsilon min. So we have our load cases, and then with edit we can insert the specific wind load in the specific load case. We need 4 different load cases, one for each direction, because then when we go on combinations, we can go on general settings, and we see that each load case for wind has its own C for combinations, and most important, they are all considered exclusive to each others. So basically, you cannot have wind in multiple directions, but only in one for each combination. They are all defined as short-term actions, and this is it. Now we can generate the combinations. And then we are done. But before running the analysis, one other thing that is very important for steel structure and is the on the input data context structure data design criteria. Here you can define the design criteria, so the specific coefficients and other numerical values used in analysis. And the most important things for the steel structures are what is called buckling length. So the length that the program should use to calculate the buckling and basically the movement of each element. You can see them in these tabs: steel columns and steel beams. So you can see that for each direction intended as a local axis, so 1, is main axis, 2, and 3, are the other orthogonal axes that if you active the vision, the view of the local axis, you can basically check them. But for each local direction, local axis, you can define the buckling length. So by default, the program see the columns as how to say, shelves. I don't know if in English for engineering is the correct term. Let's say that the program always consider the columns as fixed on the base and free on the top. So their buckling length is considered automatically as double the length of the element. Like for example, by default is 2 multiplied per L, where L is the length of the element. And this is for each element. So this is what the software does by default, but you can also define a value. So let's say that if, like in this case, we have a column that is cutted by a node at a certain height. So the program is gonna use a buckling length for this element that is equal to double the length from here to here, and for this small piece another length that is equal to the double of the length from here to here. Of course, is up to the designer to decide if this is correct or not. But let's say that you want to use the same length for the whole element. So basically, let's say that this column is 350 centimeters height. So I want a buckling length equal to 700. Now, what I have to do is to go on structure data design criteria. I have to create a new one, a new design criteria. Well, actually, no. Let's say that I want to do this for every column. I can just, in steel columns, select or better, write down 700 and 700. Or if you think, for example, that we consider the columns not fixed to the ground, but with a 3 degrees of freedom outside this plane. No, sorry, in this plane. We can use the 33700 and the 22550, that is basically not double, but the real length. So we can write different values. When the software sees a value different from 0 here, now it considers only this and not this one. So beta assigned is considered only if we have 0 on beta pre assigned, but if you write something there, this is the value considered for the software. And then we can go apply. For the beams, we can say the same basically. By default, they are considered automatic beta per L, where beta is 1. So basically, each element has its own length as backing length. As the same way as columns, we can modify that. Let's say that for the inferior current of our composite beam, we want to have a unique buckling length that goes from there to there. We can change the value, basically, as we already done for steel structures, for steel columns, sorry. And okay, this is a really important thing to care about when we're talking about steel structures. And if you want, for example, to consider the inferior current with a full length from there to there, but we want the superior current to calculate the buckling length for each single piece, we should generate a new design criteria. Here, modify the beta length, and then assign these specific criteria, so the number 8, only to the elements of the superior current. But this is a specific case now. I'm fine with that. I'll just move on with this. I hope you understood this, because it's quite important. Otherwise, just also you can ask me, send me a mail, and I'm gonna try to explain it better. So. No, we're fine. We've seen all the loads and the design criteria for what concern buckling length. Now basically we can go on and proceed with the analysis. So load assignment, we can go check load, saving data perform, or just click perform analysis. So what does happen here? The software told me that he didn't find any kind of results, so probably I set something wrong with the fixes, with the external boundaries. Sorry, let's go check them. Yes, okay, this is absolutely wrong. I'm sorry, because I basically freed the translation on X, but doing this for each node, the structure will move indefinitely in X direction. What I wanted to modify to free is the rotation around the epsilon axis, so in the X plane. Okay, so this is correct. And okay, as before, set. Now I can go properties, select off from node boundary, and then assign reference. Okay, now we see that each node has a different color. So before we had a green triangle, now we have a blue triangle. Green stands for translation and blue for rotation, red for both. And so now this could be good. Okay, overlapped are fine. Okay, so this was the problem. I'm sorry about that. And now we're done. We have our analysis. We can go and view results from the view result context. So I'll be fast on that, because as I already showed you with this command, you can so with this window on the report, you can see basically some properties, some values for each seismic load case, like the frequency for each mode and the excited mass total in each direction. But we can just close this, and basically when you view results, you can view them in 3 different ways. So for single load case, for combination and for dynamic mode. Let's do an example. Some kind of results you can see are first of all the base actions. Okay, so when I click it, basically for the self weight, the program give me the fx results at the base of the structure. Of course, they're opposite node to node. We can move results from linear analysis. Linear analysis results are okay. This is something that I should have said before. When you use non-linear elements as tension truss, this works only with combinations. When you see the results for the singular load case, non-linear elements like tension elements are just considered as normal linear elements, so like truss. So I repeat it. Non-linear elements works as non-linear only in combinations, so only when combined. If you see the results for the single load case, non-linear elements are considered as normal trusses that works both in tension and compression. So each time the software gives you this warning, but it's not a problem. Basically, we can just move to combination. And okay, you can see the fx structure reaction, F epsilon, the rotational, and this is it. I don't know if I already showed you this, but if you can select the nodes, and then with a right click here on map, you can go statistics, and the program is going to show me the maximum value for the single result, so for the single force, the minimum one, the medium one, and the total sum. So, for example, if I move to a seismic load, a seismic combination, I can see the total from here of the force applied, horizontal force applied to the structure. And okay, other kind of results when building for structure are important. The displacement. This command is just for nodes displacement, so I can go zeta translation, and we can see basically the translation for each node to see basically if the structure moves too much, because this is a natural problem basically for steel structures. And so this command is important for this on zeta, on x, and on y. Of course, on x and y they're lower, but for z, especially when we have long length and between a column and the other one, these values can go maybe too deep. Other things we can see, of course, for linear elements, for the two elements, we can see the axial action. You see that on columns and, of course, on steel frames. Axial actions, shear 2 and shear 3 is the shear force in the direction 2 or 3 based on the local axis for the single element. Torsion, bending around the axis 2 and around the axis 3, and etc. etc. These are tension and actions on the free elements, but we don't have the free elements in the structure, so we can move on. These are results for solid elements, so for bricks, and with deformation we can see the deformed shape. This is especially used with combined, let's say, with the view dynamic command, this one, in which you can basically see for each seismic mode which is its shape. And okay, if you go on combination, you can also see the deflection That is basically the maximum movement for each element, but it's quite the same. Then use this command as I showed before. So for results, this is everything. Okay, of course, you can use min and max commands to search between all combination which are the minimum and the maximum values. These are for deflection, but you can also do that like for fraction or for displacement. Let's say that I go on zeta translation for each node with with combination with max. I can check with the combination, gives me the maximum zeta translation. Where this, of course, we have as maximum, we always have 0 because the structure never moves on the positive direction of the z-axis. So we have to use a minimum. Exactly. We have a maximum but minimum value, maximum negative value. That basically is the worst case for our structure. Okay, for results, I think that we don't have that much to say. I think it's quite easy to understand and you can just try them. And what I care about is the assigned design data context, in which now we have to do the checks for our stick structure. So as before, I can go select all, right click, design, limit states. Okay, the software is warning me that there are some elements with high slenderness, but suggests me to control free length and inflection definition. That is the buckling length that I intended before when I explained you. We can go okay, it's not it's properly referring to the braces, and but now design are done. We can just use this command to see the results for still in the limit states. Okay, now everything is verified. We used quite big profiles with quite a little structure, so this is easy to check. But what can I show you there is that, of course, you can see different kinds of results. For example, with slenderness, buckling, I can see the buckling length for each element. For example, we see that for columns it is 700. That is the value that I used, I inputted on the design criteria. And then basically it's needed to check these values if they're correctly taken by the program. We can ultimately limit state check the values for each element. They're all under 1, so we're fine. The percentage use of each element. So in this case, we see that of course the central truss beam is the most loaded and also so the most used by the structure. And what else? Basically this also here I suggest you to just try each kind of results basically. And with check you can move to elements and see the specific results for each specific check. Here we have a recap in which for each status, so shear, strength, bend torsion, stability, etc., it said me if it is verified or no. So we can then move, let's say that the shear checks are not verified. We can then move to check shear and torsion on seismic cases and just see what happened. And with this we can move from node to node. And if we move to a node in which we have a connection, we can use this command, export check draw, and go connection structure drawing. Doing that, this program, ProCAD Node in Acciaio, is gonna open, and with this program, basically, you can do the specific checks only on the steel connections. So here the program automatically gives me the view of the connection of the element, also in the specific node that I selected. This program, so ProCAD Node in Acciaio, automatically imports actions from ProSAP. In fact, if I go on Carichi, we can see this table in which for each combination is reported every kind of action acting on the node. You can modify it, but it's not required basically because they're good like that. We can go OK. I'm sorry that this software is Italian only. It has no English translation. But basically from down here you can edit the geometry of the joint. So you can just click edit geometria unione. From here you can modify, for example, which is the total height. You can see here on the drawing. You can also click on lines to directly move the position. Confirm. Of course, if I click it, I can also modify it like this. I can write the exact number, and etc. etc. I can decide to embiggen this value. Okay, maybe on this you can just click on these lines, but you cannot click on this. So if I want measure height, I go 150. Now you see that the joint is bigger, but basically you can do that. Other things to say here is that of course then you can do the checks on these connections. So you can go on Verifica. From here you can select some different let's say parameters for the check. Here from Relazione you can decide which kind of relation of relazione you want. Unluckily also this is only in Italian, and here you can modify the principal factors used for the moment, for the material, sorry. And then if you click on Verifica, the program is gonna give you this short relazione in which each check is reported with these values and all the drawings from the program. So you can save it. Now I'm gonna close it. Of course, from here you can also generate the XF file. You have to save, yes, and this window works exactly as I already showed you for the drawings for concrete structures. So you have to click it, move to the right, and then click generate and save it somewhere. So okay, this was ProCAD Node in Acciaio. I'm going to say yes, and let me think. Basically this is it. Something else I can show you is that with context we can go on generate computations. I didn't show you this for concrete structures because basically what this command does is just to insert the cubic meters of material divided amongst different kinds of elements. For example, here with the steel structure, we have the total weight of all the columns, all the beams, and all the trusses, and the reinforcement, but in this case we have no reinforcement. Now you can insert a value in euro per kilonewton, and doing this you can click update and the software automatically gives you an approximation, of course, of what is or should be the total cost of our structure. With export data, you can export a CSV file with basically this table reported. As I was saying, this command works very well for steel because basically you have one material that is steel, but with reinforced concrete, it doesn't report me the amount of steel basically used for the rebars. So this is an estimation just for the concrete itself, but for a more specific cost table, you have to use the one that basically is automatically generated by the drawings. Okay. And basically this is everything for steel structures. At least the most important things that I think you should absolutely know. Of course, if you already have other questions or if something that I explained wasn't really clear, you can always ask me, send me a mail or call me, and I can explain you better or just talk about it. So see you soon in the next video.